Hello everyone, this is Fares Mzouri from the University of the Basque Country. Today I will be presenting our paper submitted to the 11th International Renewable Energy Congress, IREC 2020. The paper is entitled ANN Based Wells Turbine Airflow Estimation for Airflow Control in Oscillating Water Columns. The paper is authored by me, Fares Mzouri, Itascon Garrido and Heitor Garrido from the University of the Basque Country UPV, and Matilde Santos from the Complutense University of Madrid UCM. The presentation is organized as follows. We will start with an introduction to describe our research work. Then we will present the modeling of the different subsystems of the oscillating water column system. Then we will explain the stalling behavior problem in Wells turbines, and for that problem we will present the proposed artificial neural network airflow control. After that, we will give some results on the performance of the proposed control. And finally, we will finish the presentation with some concluding remarks. Among the myriad of systems proposed for extracting power from ocean waves, the oscillating water column (OWC) is the most reputed and exploited. Neuradia is a wave energy harnessing project installed in the breakwater in the harbor of Motrico in the northern coast of Spain by the Basque Energy Agency (EVE) since 2011. The wave power plant is formed of 16 units of OWC. Each contains a turbogenerator module of 18.5 kilowatts. Many research and studies were conducted and proposed in order to control and optimize the power output of the plant. In this context, the research work presented deals with the modeling and the artificial neural network airflow control of the OWC plant. Moving on to the OWC system modeling. The OWC consists of two main parts. The first part is the PTO, which is the power take-off system containing a doubly fed induction generator driven by a Wells turbine. The second part is the capture chamber, which is an enclosed chamber with an opening below the sea level to harness the energy of incoming waves. The oscillation of the waves will compress and decompress the air in the top of the capture chamber, causing the turbogenerator to rotate and produce electrical power. The first thing to model is the wave input. There are many wave theories in the literature, like the Stokes theories, the cnoidal wave theory, the stream function wave theories, etc. But in this work, we use the Airy wave theory, which neglects friction losses, turbulences, and other energy losses. The Airy theory is sufficiently accurate for many engineering applications, and for this theory, the wave model is described as a function of wave amplitude A, wavelength L, wave period T, and water depth H. To customize the wave model to the waves at Motrico, its representative wave spectrum has been taken into consideration to set the parameters of the model. Using the Airy theory, the temporal variation of the wave can be defined as follows. When adding the spatial dimension to the wavefront, the expression becomes this way. And by substituting the wave number k, the wave model expression becomes this way. Moving on to the capture chamber model. Using the water volume, we can express the air volume as the capture chamber volume minus the water volume. When integrating the orthogonal variation of the water surface along the area of the chamber, we obtain this expression. And by considering the chamber's geometry, we obtain this expression. Hence, we can define the volume flow rate by this equation. And finally, the actual flow rate can be defined by this expression Vx of t. Let's now see the Wells turbine model. The pressure drop across the turbine's rotor can be defined by this expression. The output is the torque, which is described by this equation. The flow coefficient of the Wells turbine is defined by this equation. And the flow rate can be written as this expression Q. The turbine efficiency of the Wells turbine can be calculated as follows. Now, the doubly fed induction generator model. The stator voltages in a B-phase frame are defined by these expressions, and the rotor voltages in a DQ frame are defined by these expressions. The stator flux are defined as follows, and the rotor flux are defined by these two equations. Then we have the electromagnetic torque and the mechanical equation relating the torque to the rotational speed. Now let's explain the stalling phenomena. The Wells turbine under study is known for its characteristic drawback, which is the stalling behavior. The stalling behavior occurs when the turbine rotates faster than the generator. This may be explained by the characteristic curve of the Wells turbine featuring the torque coefficient versus the flow coefficient. In this curve, we can see that after a critical value of the flow coefficient 0.3, the torque coefficient will start to decrease drastically, and this will decrease the produced torque. Knowing that the flow coefficient expression is as a function of the airflow speed divided by the rotational speed, it is clear that we have to control the airflow speed. The airflow speed within the turbine duct varies with the oscillating waves. In fact, the higher the wave amplitudes are and the smaller the wave periods are, the stronger the waves will be, and hence will have a higher airflow speed. This high speed will provoke the stalling behavior because the generator can't keep up with this velocity. A simulation in the uncontrolled case with 2C conditions shows the impact of the stalling behavior on the mechanical output. For this, we consider two waves. The first wave is with a wave amplitude of 0.8 meter, which is in blue, and the second wave with a wave amplitude of 1.25 meters in red. We can see that the obtained flow coefficient from the Wells turbine model exceeds the threshold value 0.3 with the second wave. Hence, the produced torque is affected by the stalling behavior at the crest of every oscillation. This will lower the torque in terms of average value. The stalling behavior may be avoided by regulating the actual flow speed. This is achieved by controlling the air valve located at the top of the capture chamber. A controller will regulate the measured airflow to a reference value provided by an artificial neural network trained by data obtained from an acoustic Doppler current profiler. The proposed control is based on a PID controller. The input of the controller is the error between the reference airflow and the measured airflow. The output of the controller is the control signal of the air valve. The valve will rotate according to the desired airflow speed. An artificial neural network has been adapted for this control to generate the reference speed Vx, since it has the ability to mimic any complex behavior without the specific knowledge of the relationships between the input data and the target data. The ANN will be trained to recognize incoming waves from measured data gathered by ASTI Tecnalia at the breakwater of Motrico in the northern coast of Spain. Both inputs of the designed ANN are obtained from the acoustic Doppler current profiler installed at the breakwater of Motrico. The designed artificial neural network will estimate reference airflow speed values for all wave amplitudes and periods, but will also recognize the strong waves and will provide reference values to limit their airflow speed in order to avoid the stalling behavior. An artificial neural network consists of neurons in the input, output, and hidden layers, connected with wave signals. The neurons consist of a bias value, a sum function coupled to an activation function. The sum function may be defined by this equation. The proposed network for the airflow control is a multi-layer perceptron structure with 2 input neurons and 1 output neuron. The update expression of the weights are defined by this expression. The network has been trained using Levenberg-Marquardt algorithm, which aims to minimize the performance index by weight correction, defined as follows. The mean squared error has been chosen as the criterion for the artificial neural network model to be used in the proposed airflow control. Numerous artificial neural network structures were trained and tested with the wave data for airflow speed estimation, and the best MSE has been recorded. From this table, we can see that the best MSE has been obtained with ANN1 and ANN2, and for this reason, we will further investigate the performance of these two structures. When observing the training performance of both ANN1 and ANN2, it is clear that ANN2 managed to provide better performance at 137 epochs. Hence, for the proposed ANN airflow control, the structure ANN2 has been selected. Now let's see the performance of the proposed control with the selected ANN structure. Using the models or the subsystems of the OWC mentioned earlier, we implemented this wave-to-wire model on MATLAB Simulink. We configured the model with parameters obtained from the Nereida wave power plant in Motrico. To test the control, we used two waves. The first wave with a 0.8 meter wave amplitude, followed by a 1.3 meter wave amplitude. The obtained flow coefficient in the uncontrolled case with the second wave exceeds the threshold value. This activates the airflow control in the controlled case, and the flow coefficient then has been adjusted to 0.3. This is thanks to the artificial neural network airflow generator, which stopped the strong airflow as shown in this figure. The obtained torques avoided the stalling effect and maintained higher values. Hence, the resulting generated power is higher in the controlled case than the uncontrolled case as shown in this figure. So to conclude, in this paper, an oscillating water column plant has been modeled and controlled by an artificial neural network airflow control strategy to avoid the stalling behavior and improve the generated power. The designed artificial neural network has been trained using real wave data gathered by an acoustic Doppler current profiler at the site of Motrico. The plant model and control were tested under sea conditions provoking the stalling behavior, and results show successful avoidance of the stalling behavior and power improvement. The developed OWC model serves our research to implement and investigate other control strategies for a stalling-free operation. Thank you very much for your attention.